Imagine drifting alone through the endless darkness of space. No sound, no wind, no up, no down, just silence. Then you see it. At first, it doesn't look dangerous. There's no explosion, no fire, no warning, just a perfectly black circle floating in the darkness. But that silent shadow is unlike anything else in the universe. It bends space, it bends time, it traps light itself, and once you cross a single invisible boundary, there is no escape. Not because you're moving too slowly, not because your spacecraft has failed, but because the laws of the universe themselves have turned against you. So, what would actually happen if you fell into a black hole? Would you be torn apart in an instant? Could you survive longer than scientists once believed? What would you see as the entire universe changed before your eyes? And what, if anything, waits beyond the event horizon? Today, we're about to take the journey that no human has ever survived to describe. Before we begin our journey, we need to answer one important question. What exactly is a black hole? Despite what movies often show, a black hole is not a giant cosmic vacuum cleaner endlessly pulling everything in around it. In fact, that's one of the biggest myths about black holes. If our sun were somehow replaced by a black hole of exactly the same mass, something surprising would happen. Earth would not suddenly be swallowed. It would continue orbiting exactly as it does today. Why? Because gravity depends on mass, not on whether an object is a star or a black hole. A black hole only becomes dangerous when you get incredibly close to it. But if it isn't some kind of cosmic monster, then what is it? To understand that, we need to travel billions of years into the past. Somewhere in our galaxy, a star is born, not an ordinary star like our sun, a giant, a star dozens of times more massive than the sun. For millions of years, this enormous star shines brightly. Deep inside its core, nuclear fusion creates an incredible amount of energy. That energy pushes outward. At the same time, gravity pulls everything inward. As long as these two forces remain balanced, the star survives. But nothing in the universe lasts forever. Eventually, the star begins to run out of fuel. Fusion slows down. The outward pressure weakens. Gravity finally gains the upper hand. In just a matter of seconds, the core collapses with unimaginable force. The outer layers explode into space in one of the most violent events in the universe, a supernova. For a brief moment, this explosion can outshine an entire galaxy. But the real story is happening at the center. If the remaining core is massive enough, nothing can stop the collapse. Not light, not matter, not even the fundamental forces that hold atoms together. The star keeps shrinking, smaller, denser, hotter, until an extraordinary object is born, a black hole. Imagine squeezing the mass of several suns into a region no larger than a city. The result is gravity so powerful that it doesn't simply pull on objects, it bends space itself. According to Einstein's theory of general relativity, gravity is not an invisible force reaching across space. Instead, massive objects curve the fabric of space and time. Planets orbit stars because they follow these curves. But a black hole creates the deepest curve imaginable. Near its center, space and time become so distorted that every possible path leads inward. There's only one direction left to travel, deeper toward the center. Surrounding every black hole is an invisible boundary known as the event horizon. Cross this boundary and escape becomes impossible, not because something is physically pulling you back, but because every possible future now points toward the center of the black hole. Even light, the fastest thing in the universe, cannot find a path back out. And if light cannot escape, neither can you. But reaching the event horizon is only the beginning, because what happens next is far stranger than most people now could imagine. That you are the first human ever sent on a mission to a black hole. Your spacecraft is equipped with the most advanced technology humanity has ever built. Every camera is recording, every sensor is collecting data, and billions of people back on Earth are watching your journey live. At first, nothing seems unusual. The black hole appears as nothing more than a tiny dark circle against a sea of distant stars. It doesn't flash, it doesn't roar, it doesn't announce its presence, it simply waits. As your spacecraft moves closer, something strange begins to happen. The stars behind the black hole no longer appear where they should. They stretch, they bend, some even seem to form glowing rings around the darkness. It almost looks as though the universe itself is being twisted. And in a way, it is. According to Einstein's theory of general relativity, gravity doesn't simply pull on objects. It bends the very fabric of space and time. Light always follows the shape of a space. So when space bends, light bends with it. This incredible effect is known as gravitational lensing. The black hole acts like a gigantic cosmic lens. It warps the light coming from distant stars and galaxies, creating strange distortions that seem almost impossible. You are no longer looking at the universe as it truly is. You are looking at the universe through space that has been twisted by gravity itself. But something else catches your attention. Surrounding the darkness is an enormous ring of brilliant light. It shines brighter than entire galaxies. Brilliant shades of white, gold, orange, and deep blue swirl around the black hole at incredible speeds. This is not the black hole itself. It is something called an accretion disk, a vast river of gas, dust, and shattered stars trapped by the black hole's immense gravity. As this material spirals inward, it begins to collide with itself. Those collisions generate enormous amounts of friction. Temperatures climb to millions of degrees, hot enough to produce powerful X-rays and some of the brightest light in the entire universe. Ironically, one of the darkest objects ever discovered is often surrounded by some of the brightest regions in existence. From a safe distance, the sight is breathtaking, beautiful, peaceful, almost hypnotic. But appearances can be dangerously misleading. Every second, your spacecraft is moving closer, gravity is growing stronger, and ahead of you lies an invisible boundary that no one has ever crossed and returned from. The event horizon, the point where the rules of the universe begin to change forever, and your journey is only just beginning. A force powerful enough to stretch stars, tear apart planets, and transform the human body into something no one could survive. And that is where our journey truly begins. You're seconds away from crossing the most dangerous boundary in the universe. Everything you've seen so far has only been the beginning, because beyond the event horizon, no one knows exactly what awaits you. The greatest minds in history have tried to answer that question, but none of them have ever been able to test it. Until now, let's keep going. You're seconds away from crossing the most dangerous boundary in the universe. Everything you've seen so far has only been the beginning, because beyond the event horizon, no one knows exactly what awaits you. The greatest minds in history have tried to answer that question, but none of them have ever been able to test it. Until now, let's keep going. Your spacecraft continues forward. The event horizon is now only moments away. There is still no explosion, no shockwave, no warning lights, just silence. Looking through the front window, space seems almost normal, but behind you, the universe is beginning to change. The stars no longer appear fixed. Their light bends into impossible shapes. Entire galaxies seem stretched across the darkness like glowing ribbons. Every second, gravity tightens its grip. Yet inside the spacecraft, you feel nothing, no crushing force, no sudden acceleration, only the quiet hum of the engines. And then, without any dramatic sign, you cross the event horizon. Nothing happens. At least, nothing you can feel. This is one of the strangest predictions in modern physics. If the black hole is massive enough, crossing the event horizon may be completely uneventful. There is no invisible wall, no burst of energy, no cosmic barrier. You simply pass a point from which every possible path leads deeper inside. By now, there is no possibility of turning back. The universe you once knew has disappeared forever. Ahead lies only darkness and a destination no human has ever reached. But even after crossing the event horizon, your journey has only just begun. And now, gravity begins to reveal its true power. The force pulling on your feet becomes slightly stronger than the force pulling on your head. At first, the difference is tiny, almost impossible to notice, but every kilometer you fall, that difference grows. These are called tidal forces. They don't simply pull you downward, they pull different parts of your body with different amounts of force. Imagine stretching a rubber band. Slowly at first, then harder and harder. If the black hole is relatively small, these tidal forces become overwhelming long before you reach the center. Your spacecraft begins to deform. Metal groans, bolts snap, panels twist under unimaginable stress, and eventually, your body would begin to stretch as well. Scientists have given this terrifying process an almost humorous name, but there's nothing humorous about it. Every bone, every muscle, every cell would be pulled into an ever thinner stream of matter by gravity that changes dramatically over incredibly short distances. Far away, billions of people are still watching your mission, but to them, something impossible is happening. Your spacecraft appears frozen in time. Every movement slows. Every signal takes longer to arrive. The light from your ship grows weaker, redder, dimmer, until it fades almost completely. To every observer outside the black hole, it looks as though you never crossed the event horizon at all. Your image simply lingers, forever approaching the edge. This isn't an illusion. It's the result of gravity stretching time itself. From their perspective, you become trapped at the edge of time. You keep falling. There is no sensation of speed anymore. Outside, the universe has vanished. Inside, only darkness remains. For decades, the singularity has been described as a point of infinite density, a place where all the mass of a black hole is compressed into an infinitely small volume. According to Einstein's general theory of relativity, this is where every path through the black hole comes to an end. Gravity becomes infinitely strong, space-time becomes infinitely curved, and our equations produce infinite values. But physicists have learned to be cautious whenever mathematics predicts infinity. In science, infinities often signal that a theory has reached the limit of what it can describe. General relativity has passed every experimental test we've been able to perform. It accurately predicts the motion of planets, the bending of light, the expansion of the universe, and even the existence of black holes themselves. Yet inside the singularity, the theory breaks down. It no longer tells us what reality actually looks like. Instead, it tells us that something important is missing. Imagine using a map that ends at the edge of a forest. The map doesn't prove the forest ends there. It simply means the map can take you no farther. The singularity may be much the same. It may not be an infinitely small point at all. Instead, it could represent a place where quantum physics becomes more important than gravity alone, a region where our current understanding of nature is incomplete, somewhere beyond the reach of today's equations. This is why physicists continue searching for a theory of quantum gravity, a theory capable of combining Einstein's description of gravity with the strange rules of quantum mechanics. Until that theory exists, no one can say with certainty what truly lies at the heart of a black hole, and that uncertainty may be the greatest mystery in the entire universe. The moment you cross the event horizon, nothing dramatic happens. There is no flash of light, no explosion, no invisible wall announcing that you've entered another realm. If your black hole is supermassive, you may not even realize you've crossed the point of no return. Everything inside your spacecraft appears completely normal. Your heart is still beating. Your clock still measures every second. Your breathing remains calm. Yet something profound has changed. Every path that once led back to the universe has disappeared. Imagine standing on a mountain where every road leads downhill. No matter which direction you choose, you always descend. Inside a black hole, space behaves in a similar way. Outside the event horizon, you can choose to move forward, backward, left, or right. But once you cross that invisible boundary, every possible future points toward the center. Moving toward the singularity becomes as unavoidable as moving toward tomorrow. You cannot stop it. You cannot avoid it. And no amount of technology can change your destination. Even if your spacecraft had engines capable of producing unlimited thrust, escape would still be impossible. Not because you lack speed, but because there is simply no path that leads back out. The very geometry of space-time has changed. From your perspective, you continue falling. There is still no sensation of crossing into another universe, no sudden darkness, no mysterious portal opening before your eyes. The universe outside grows increasingly distorted. Light arriving from behind you becomes compressed into an ever smaller region of the sky. Every star, every galaxy, every memory of home slowly fades into a shrinking circle of light. Ahead, there's only darkness. And somewhere within that darkness lies the destination every object inside a black hole must eventually reach, the singularity. Whenever science reaches the edge of knowledge, imagination quickly follows. Could a black hole be more than a cosmic trap? Could it be a doorway? One of the most fascinating ideas comes from Einstein's own equations. Certain mathematical solutions suggest the possibility of a bridge connecting two distant regions of space-time. These hypothetical bridges are known as wormholes. Imagine folding a sheet of paper. Two distant points suddenly touch. Instead of traveling across the entire surface, you pass straight through. If wormholes exist, they could, in theory, connect opposite sides of our galaxy, distant galaxies, or perhaps even entirely different universes. It sounds like science fiction, but the mathematics allows for the possibility. The challenge is keeping such a tunnel open. Every known calculation suggests that a traversable wormhole would collapse almost instantly. Preventing that collapse may require a form of exotic matter with properties we have never observed in nature. So while wormholes remain mathematically possible, there is currently no experimental evidence that they exist. Another mysterious prediction is even a stranger: a white hole. If a black hole allows matter to enter but never escape, a white hole would do the exact opposite. Nothing could enter. Everything would be forced outward. Matter, light, and energy would constantly emerge from it. White holes appear in certain theoretical models of general relativity. Yet despite decades of observations, astronomers have never found convincing evidence that a white hole exists anywhere in the universe. They remain one of physics' most intriguing possibilities. Ideas waiting for evidence, questions waiting for answers. For more than a century, Einstein's general theory of relativity has been one of the greatest achievements in human history. It predicted black holes long before anyone had ever seen one. It explained why light bends around massive objects. It revealed that time itself can slow down, and every major prediction has been confirmed by observation. Yet here, deep inside a black hole, Einstein's masterpiece reaches its limit. The equations begin producing impossible results: infinite density, infinite curvature, infinite gravity. In physics, infinity is usually a warning sign. It doesn't necessarily describe reality. Instead, it tells us that our mathematical model is no longer complete. Imagine using a world map to navigate the surface of Earth. It works beautifully, every continent, every ocean, every country. But the moment you try to use that same map to describe the inside of an atom, it becomes useless. Not because the map is wrong, but because it was never designed for that purpose. General relativity faces the same problem. It describes the largest structures in the universe with astonishing precision: galaxies, stars, planets, even black holes. But at unimaginably tiny scales, another set of rules begins to dominate: the strange world of quantum mechanics. Here, particles behave like waves, empty space constantly fluctuates with energy, and certainty gives way to probability. The problem is, these two great theories refuse to cooperate. General relativity describes a smooth, continuous space-time. Quantum mechanics describes a universe built from tiny, uncertain events. Both theories are extraordinarily successful, yet when combined inside a black hole, they contradict one another. That is why physicists continue searching for something even deeper: a theory of quantum gravity, a theory capable of describing gravity at the smallest possible scales. It could explain what really happens at the center of a black hole. It could reveal what existed during the first moments after the Big Bang. It might even rewrite our understanding of space, time, and reality itself. But despite decades of research, no one has found the final answer. Some of the brightest minds on Earth continue searching, and for now, the heart of every black hole remains hidden behind equations that simply stop working. Our journey is almost over. We began by asking a simple question: what would happen if you fell into a black hole? Along the way, we discovered that gravity can bend light, slow time, stretch space itself. We crossed the event horizon, where escape is no longer possible. We reached the edge of Einstein's understanding, and stepped into a place where even the greatest theories begin to fall silent. Beyond this point, certainty disappears. Mathematics gives way to mystery. Questions become more powerful than answers. Maybe one day, humanity will build a theory capable of explaining what truly happens inside a black hole. Maybe future generations will discover that wormholes are real, that information is never lost, or that the universe is far stranger than we ever imagined. Or perhaps some places were never meant to reveal their secrets. Black holes remind us that no matter how much we've learned, the universe is still filled with mysteries waiting to be explored. And maybe that's what makes it so beautiful, because every answer we discover leads to an even greater question. So, if you ever found yourself drifting toward a black hole, remember this: the greatest danger isn't simply that you might never return, it's that you may become the only witness to a part of reality that no one else will ever see. Maybe no human will ever know what truly lies beyond a black hole, because once you cross the event horizon, every answer disappears with you. Until then, the universe keeps its greatest secret hidden in the darkness. We've traveled farther than any human ever could. We've crossed the event horizon. We've watched space and time bend beyond recognition. But perhaps the greatest mystery of all has nothing to do with gravity. It has to do with information. Imagine throwing a book into a black hole. The pages disappear, the words disappear. Eventually, even the atoms that made the book seem to vanish forever. According to Einstein's theory, everything simply falls beyond the event horizon. But quantum mechanics tells a very different story. In the quantum world, information cannot simply disappear. It may become scrambled. It may become almost impossible to recover. But the fundamental laws of quantum mechanics suggest that information is never truly destroyed. So what happens when something falls into a black hole? Does the information survive, or is it erased forever? This contradiction is known as the black hole information paradox. It has challenged physicists for nearly half a century. Then, in 1974, Stephen Hawking made an extraordinary discovery. Black holes, he realized, are not completely black. Because of quantum effects near the event horizon, they should slowly emit tiny amounts of thermal radiation. Today, this is known as Hawking radiation. Over unimaginable periods of time, a black hole could gradually lose energy, shrink, and eventually disappear completely. But that only deepens the mystery. If the black hole eventually evaporates, what happens to everything that fell inside? Does the information escape with the radiation? Is it somehow stored on the event horizon itself? Or have we misunderstood one of the most fundamental laws of physics? Modern theories offer several possibilities. Some suggest that information is subtly encoded within Hawking radiation. Others propose that it is preserved on the surface of the event horizon through a concept known as the holographic principle. Some physicists even speculate that the interior and exterior of a black hole may be connected in ways we don't yet understand. Despite decades of research, no single explanation has been proven. The paradox remains one of the deepest unsolved problems in modern science.